Hello, everyone. Good morning, good afternoon, good evening, depending on the time zones you are in. So welcome to yet another webinar of Trevor Platt Science Foundation. I know that we are meeting for a webinar after a gap of 6 months. So welcome to today's webinar on oceans and marine ecosystems, amplifiers or attenuators of global warming, organized by Trevor Platt Science Foundation and hosted by the Air Center, Portugal. Today's speaker is Dr. Raghu Murtugudde. I would describe him as a versatile personality. He's an aerospace engineer, a climate scientist, YouTuber. Many of you are familiar with his YouTube channel, the Murtugudde Climate Academy, through which he educates young students as well as the common people on climate science. He's an author of high-impact scientific papers, at the same time writes popular articles on climate change issues. His formal biography and achievements are listed in the webinar announcement. What I found interesting on his LinkedIn profile was the way he described life. He says that he enjoys the hikes and cups of tea that he manages to squeeze in between the busy climate education schedule. So here we have a quick-witted personality, Dr. Raghu Murtugudde. Welcome, sir. Over to you.
Thank you, Nandini. Thank you, Shubha. Thank you, Jose, for this opportunity. So I'm going to start sharing. Can you see my PowerPoint? Okay, are we good?
You're good.
All right. So since this is supposed to be about motivating young people, I'm going to jump right in. I'm going to cover a kind of range of topics, different time scales and different spatial scales and physics and biology focused on the ocean. So I won't spend too much time on introduction, and this is not something very specific to my research, even though it's based on some of it, but these are broader questions. And just to orient ourselves, we know that sun's energy is coming in mostly as visible, and it's heating land and the oceans, and oceans have higher heat content and they are deep, so they warm up slowly, cool down slowly, whereas land warms fairly quickly and cools down quickly as well. And the entire problem is about heat balance. Because we are on a sphere, we have less energy being received per unit area at higher latitudes than in lower latitudes. And we, for that reason, cool the higher latitudes, and then you have ice and snow, and we have high albedo. So when you look at the thermal energy going out of the system, think of the pot which is getting hot. You cannot see the heat coming out of it, but if you go close, obviously you know there is thermal energy coming in. We have not evolved to see thermal energy with our eyes, but many animals have, and of course our soldiers can see it when they wear their infrared goggles and so on. So this creates equator to pole temperature and energy gradient. So we all know from the basics that the incoming solar is much less than the outgoing long wave radiation or thermal energy at higher latitudes, and vice versa. So we have excess energy in the low latitudes and deficit energy at high latitudes. From observations, we know that poles are not getting colder and colder, and lower latitudes are not getting warmer and warmer. So we are moving energy from low latitudes to high latitudes all the time, and this is done through winds, and then winds force the ocean, which creates clouds, rainfall, and then vegetation response happens, and so on and so forth. So on evolutionary time scale, things have evolved, plates have moved around, and we are in this current configuration. And this is about what we understand very well, that greenhouse gases are very important to trap the outgoing long wave energy. So how much goes out and how much is trapped depends on this blanket we have. We call it the Goldilocks syndrome. We have the perfect blanket compared to, let's say, Venus or Mars. Venus is too hot, Mars is too cold, and we assume that we have the perfect environment for life and so on. But beyond that, pretty much everything remains quite unknown, but not in a bad way. We do understand many things, And if you look at the sea surface temperature and land temperatures seasonally evolving, we know high latitudes are cold, and there is asymmetry in the southern polar region and the Arctic region. And the sea surface temperatures are moving north and south with the sun. And there are zonal or longitudinal asymmetries because oceans have continental boundaries and so on. And Indian Ocean is specifically very unique with its land coming down towards the equator and creating very warm waters and monsoonal circulation and so on. And obviously this shows up in terms of rainfall as well. So if you look at the so-called intertropical convergence zone and the rain bands, there are many interesting features, and monsoon circulation again becomes very different with the orography, with the ocean forcing, and so on and so forth. So what becomes very important in this sense is that the ocean has all the memory, covers 70% of the surface area, but is also very deep, high heat content. So even though sun goes up and down and sun goes north and south, we should have diurnal cycle and seasonal cycle. But because the ocean can store heat and release it at various time scales, we have literally continuous time scales from diurnal to weekly to multiple weeks, seasons, years, decades, and even centuries. And of course, there are inertia built in also in terms of glaciers and so on and so forth. So ocean obviously is the major source of water vapor. So it provides all the energy, most of the energy anyways, for climate variability, but also is becoming a big partner in creating trends and also extremes in terms of heat waves, sea level rise, floods, droughts, extreme rainfall events, and so on and so forth. So oceans obviously have a massive role to play. And yet, if you look at the distribution of temperatures and distribution of rainy bands and evaporative regions, there are many fundamental questions of scale selection that remain quite open. So for young people, it's daunting to figure out what is understood already and what is not understood, because if you start reading papers, there are literally millions of papers and you can get overwhelmed thinking everything is understood. But actually, you should pay attention to what is not said in a paper. Papers say many things and they have many references, but they always leave something open at the end. So they have a beginning and they have an end, but neither the beginning is from scratch nor the end is the end. So you have to always kind of read the papers with something missing and look for what is not said and always find your interesting questions there. So I'll point out some of those things. And often we understand the atmosphere, the ocean, the land, their interactions, climate of the past, and trying to do climate of the future with the so-called models. I won't go into details, but most of you are probably aware that models are fit on the sphere with grids in the atmosphere and grids in the ocean. There are many details, many missing understandings. We don't know how to do clouds, for example, from first principles. There are many irreducible uncertainties. We might have heard of aerosols in the atmosphere, how they can directly affect solar radiation or indirectly affect cloud microphysics. We don't talk so much about aerosols and clouds in the ocean, and yet we have marine snow, we have phytoplankton, and we have clouds of phytoplankton that affect radiation penetration, amount of heat taken up by the ocean, how long it can stay there, and how it feeds back to the coupled ocean-atmosphere interactions. So I will already start saying these things as open questions. So anytime you have questions, you can put it in the chat box, and we can take them at the end. If it's really urgent, you can stop me somehow, raise your hand or something. So irreducible uncertainties are great. But nowadays, we have so-called data-driven models. So for example, Tapio Schneider of Caltech has been funded by Schmidt Future of Google founder, where he's using data and AI to try to solve cloud problems, which have become quite a handicap for climate models. So even when you think about not understanding why the intertropical convergence zone is where it is and why it is such a narrow band, it's a great challenge, because if you don't understand the mean state, then it's very difficult to understand how it is responding to global warming. So if you want to project for the future or understand how global warming is affecting climate or how it's modulating natural variability like the monsoon or El Nino, La Nina, North Atlantic Oscillation, Pacific Decadal Oscillation, any particular mode you take, all those are now happening in a warmer world. They are being modulated by global warming. But unless we understand the basic mechanisms, often we are lost in terms of understanding what is it that is changing in the basic processes because of global warming. So models are very helpful. They're incredibly useful because just given the radiation at the top of the atmosphere coming from the sun, they are going to take the equations, first principles, Navier-Stokes equations. They have a momentum equation or Newton's law of motion, F equal to ma. They have thermodynamics, they have energy, they have all these equations are solved, and they can produce a monsoon, they can produce El Nino, climate, this and that, yet they are not always perfect. So in the ocean, for example, how the actual mixing happens remains one of the biggest challenges for physics, but this also affects how nutrients are moved around, how preformed and precipitating nutrients are cycled, how they are brought back up, how they are utilized, and how they are made available, and how biology actually responds to the physics and so on. So these are tremendous challenges, and a lot of very smart people work on ocean mixing issues, and often you feel frustrated because it's very local. You can make thousands of microstructure measurements in every place, and you don't necessarily get a unifying principle which can go into a model, because models have to run at a global scale, and you cannot put a different mixing scheme at every grid point. So you have to prescribe the mixing in some way, and you have to evolve that information out of the data that you have. And you are all lucky because now you are arriving into this field at a time where big data analytics and artificial intelligence, machine learning, and so on are available, which are kind of blind to the first principles. Just give them the data and they can tell you many interesting things. If you start with equations and first principles, you always run into a wall or some irreducible uncertainty, whereas these techniques are completely blind to the physics, and they just churn things and tell you what patterns are there, and so on and so forth. So this will advance things much faster in the coming years, and you are at the right time to pick up on many of these things, okay? So let's look at the Earth system within which the ocean and the ecosystems are functioning. Obviously, we have sun forcing, and things like volcanoes are also external forcings. Forcings very briefly means anything that perturbs the energy balance at the top of the atmosphere. Remember, sun's energy is coming in, some of it is getting reflected, and thermal energy is going out. So incoming solar minus outgoing long wave is the balance. Sun's energy is, of course, important for this balance, and volcanoes are something that are digging up material put away in the land, and they are spewing it into the atmosphere, just the way we are digging up fossil fuels and burning them and creating greenhouse gases and perturbing the radiation. So what is the big deal about the Earth system? Any system has many components, right? So you can think of your own body. You have the nervous system, digestive system, skeletal system, you have the neuronal system, and so on. Each component doesn't do much by itself, but together they make the system run. I'm speaking, I'm waving my hands, I'm looking at the camera, and I'm explaining things. All this happens because the system works together. So Earth's system is, in that sense, very, very important in terms of its feedbacks. We already talked about how sun goes up and down, but weather can change many times during a day because there are a lot of feedbacks in the system. So you have the geosphere, you have the biosphere, and you have the anthroposphere, or the human beings with their energy systems, producing and consuming things, affecting the geosphere and the biosphere directly and indirectly, and so on. So now we have become like an external forcing. We are taking out fossil fuels that are buried away from the atmosphere and the climate system, and we are putting them into the climate, so we're affecting the radiation balance. What do we do with this? I said already, whether oceans, in the title I said, are oceans and ecosystems, are they attenuators or are they amplifiers of global warming? So there is something called bioclimate feedback. In fact, Shubha was one of the first ones to work on this with satellite data in the Arabian Sea to argue that the trapping of the radiation because of the phytoplankton cloud in the ocean can seriously affect the heat balance, temperature warming, and so on. So with global warming, I'm jumping a little ahead and saying that we are changing the winds, we are changing the energy balance, we are changing rainfall distribution, and we are, of course, changing the amount of radiation coming to the surface and so on and so forth. And biology is responding. Some of you are probably already aware that we think of the ocean ecosystem as having a biological pump where the biology is moving nutrients up and down in the water column or horizontally. And we have the so-called solubility pump where the circulation, mixing, upwelling, downwelling, etc., are moving CO2 and other nutrients up and down. We have always assumed in most places that solubility pump is very dominant. But with warming, for example, you know that the surface warms more, so the stratification gets stronger, mixing the nutrients into the euphotic zone or the light layer becomes more and more difficult as surface warms and the stratification gets stronger. So how will the biology respond? We already have some idea. I will show some broad results, but we still have very little idea about how solubility pump is changing and how the biological pump is changing. You can imagine that biological distribution of species, etc., is changing, but you also have maybe with stratification, more nitrogen fixers becoming dominant in many places as opposed to those which depend on ammonium, nitrate, and so on and so forth. So many, many very complicated questions. I'm going a little fast with too many questions. If you don't understand, don't worry, they're recording it and you can listen. And for each of them, you can send me questions afterwards as well. They will give you my contact number and so on. And I have many of these things on my YouTube channel as well. So this is the first thing I will mention in terms of oceans, their role in climate change, climate trends and extremes and so on, and whether they will amplify global warming. They have been amplifying global warming, or they will become attenuators, or already if they're attenuating climate change. But first, what do we want to see? We want to see what the patterns of warming are. Okay, so we keep saying global warming is happening. This is the pattern of global warming from 1901 to 2023. And of course, there is a so-called warming hole here in the North Atlantic, and there is the polar amplification in the Arctic. Tropics warm more, the Middle East and so on are warming more. Eurasia is warming more. This region is not warming as much. But if you look at a closer period from 1994 to 2023, you can see how the pattern is emerging with polar amplification, Middle East and Mediterranean warming, cooling in the Indian region, warming over the Indian Ocean, and there is a critical cooling here as well as the cooling here. These remain largely open questions as well. For those who understand thermohaline circulation, originally it was speculated that maybe the thermohaline circulation is slowing down and that's not bringing enough warm water and causing cooling. But now it says maybe it's related to the North Atlantic oscillation. There is some work that says that the anthropogenic impact is not so strong here, but it's stronger here on the northward side. So maybe it's the Arctic connection that is changing. So basically an open question. But in terms of the ocean's role, this is a very critical region. For those who know the background state, in fact, I pointed that out when we looked at this one. See, if you look at carefully, this region here in the Eastern Pacific is much cooler than the region in the West Pacific. This is called the warm pool. This is called the cold tongue. Many of you probably already have the basic oceanography where the trade winds diverge the waters away from the equator and create upwelling and cool the temperatures. So this east-west sea surface temperature gradient is very critical. When you have cool temperatures here, the ocean is soaking up heat and putting it away. And when El Nino comes, some of it is being released, like we are right now in an El Nino, even though it's in its waning phase. So ocean is a very dynamic thermostat that can actually control global warming just in this region where the ocean dynamics brings up cold water and the atmosphere is trying to warm it. So ocean is soaking up heat like a sponge, and global warming is not as large as it could be if that was not happening. So in a global warming sense, then, if this region doesn't warm as much as this region or even cools as this indicates, then this east-west temperature gradient will get stronger. That means the pressure gradient will get stronger. That means the easterly winds will get stronger, and they will favor more upwelling, which means the ocean will take up more heat. So it's not just at the El Nino time scale, but now we are talking about decadal and anthropogenic trend time scale, that the ocean is favoring a thermostat-like behavior. The more you try to warm it, the more it is responding by saying, I will take up more heat. This is a remarkable feature of the ocean, and how the biology responds to this is going to become very critical as well. We have some idea about it, but we'll see what that means in a minute. So each time there is a lot of news, you must pay attention to the details such as these patterns. So 2023 is now being discussed endlessly, is the warmest year ever, and so on. And yet, look at the patterns. India cooled, this region warmed because it's an El Nino. So what causes these patterns? Those are the patterns that determine what happens in your backyard in terms of heat waves, extreme rainfall, lack of snowfall, and so on and so forth. So we must pay attention to the patterns, because nobody lives in the global mean temperature. Nobody lives in the global mean sea level. There are important factors, metrics to track the energy we are trapping, but you must always pay attention to the patterns and what are the dynamics that are happening here, and what is the ocean doing here. We are not only affecting the ocean at the coasts with nutrient runoffs and so on and so forth, we are affecting the ocean in very unique ways. For example, the Middle East warming here is affecting the winds over the Arabian Sea. Arabian Sea is warming because of it, and Northwest India and Pakistan are getting heavy rainfall because of it. Pakistan has been flooded every year since 2010. It's a poor country. It's getting hammered every summer monsoon season, and before the monsoon, it is getting hammered with heat waves because of what land is doing to the ocean. So we are acting on land, we are doing lots of things on land, but we are hammering ocean everywhere. Of course, you hear about ocean acidification, deoxygenation, sea level rise, and so on and so forth, right? The other big thing, even if you look at globally, if you look at Earth's energy balance, this is looking at how much energy is being trapped since this is going from 1971 to 2018, and then also being shown in parentheses are numbers for 2010 to 2018 to show that things are accelerating. So over this period, 1971 to 2018, we have created about half a watt per meter squared of extra forcing to the system. And to remove it, we need to reduce the CO2 by about 57 ppm, but let's leave it there. The total heat gain associated with additional heat flux is 358 zetajoules. Cryosphere melting takes up about 4%, atmosphere is taking up about 1%, and land is taking up about 6% of it. But if you look at 2010 to 2018, I won't go into the detail, many things are accelerating. What is the number we are interested in? Ocean. Ocean took up 89% of the additional energy from 1971 to 2018, and it took up 90% during 2010 to 2018. We are really fortunate that ocean is doing so much heavy lifting. It's paying a price in terms of warming all the way down, losing oxygen, getting acidified, and so on and so forth. But the main question is, will the ocean be able to continue to take up so much of the additional energy we are trapping? This is a critical question, and that comes down to understanding what the patterns are and what the ocean is doing and how it is feeding back to the climate system. These are difficult questions, but as young people, even if your background is ocean, it's marine biology or whatever, you should be aware of the larger scale context in which you are working. So don't get too deep down into the rabbit hole, focusing only on your tiny problem. Always keep your eye on what the bigger problems are and what the contexts are for ocean and its marine ecosystem. Of course, ocean is also taking up 25 to 30% of the CO2 we are emitting. These are the sources from fossil fuels and land use. Atmosphere accumulates some, land is taking up more and more. So atmosphere is accumulating more, land is taking up more, and of course, ocean is taking up more and more as well. 25 to 30%, as we said, of the total carbon flux as well. And if you look at the accumulated carbon, of course, ocean is accumulating more and more. So it is acidifying, but we need to figure out what the impacts are and how the ecosystems are responding. Is everybody responding negatively to acidification and warming, or are there any evidences that some species are responding okay or even thriving in warming waters? This is critical, so I will show some example of it. Okay, so always have curiosity and excitement, because the world is not really coming to an end. There are many problems, you can solve them, and there is time to solve them. Of course, we don't want to keep emitting the way we are, but we need to work harder on reducing emissions, but also finding solutions. And you are the future. The future is yours, so you need to work on these things. So this is some exciting news, for example. See the dozens of new species this deep sea robot just discovered. This is just from February 24, 2024, off of New Zealand. Many things here. One, we still don't know so much about the ocean, so many new species yet to be discovered. And we have now so many new innovations like robots, which can go deep into the ocean, where it's very difficult for humans to go, but they can happily wander around and beam back the data. Okay, so I'll come back to this later on in terms of innovations for observations that we can get involved. You also want to pay close attention to smaller scales. Let's say marine ecosystems. This is a model called macroecological theory on the arrangement of life or metal. They have various ways of defining ecological niches. The rule we always say is that nature makes the rules, biology finds the loopholes, right? So are the ecosystems some way organizing themselves into maximize, let's say, the health of the ecosystem, which is often defined as complexity or biodiversity, resilience, how they respond to perturbations, including global warming, acidification, deoxygenation, etc., and how they maximize productivity. So this idea is basically that you can go from, I have this thing I have to move. How can I minimize this thing? It's annoying here. Okay, so it's looking at environmental factor 1 and 2 and looking at abundance. And this model basically assumes that you have the genomic adoption or adaptation, and you have molecular processes, physiological processes, biological and behavioral processes together creating these niches. And abundance is assumed to be maximized to reach the ecological optimum. This is not the only model, but I'm just using it as an example. And there are, of course, environmental drivers riding on top, where each environmental interactions determine the natural selections on evolutionary timescales. But what is amazing is that evolutionary timescale is not millions of years. Many species evolve literally in 1 or 2 generations. This is what you have to understand if you are interested in this kind of topic. So this is just a model, but it tells you, oops, I'm stuck here. Okay, so this tells you from the same model how the distributions are occurring. So these are number of species. This is the surface species on land. This is the marine surface species, and these are marine benthic species. You learn the general rules that benthos is much more biodiverse because the ecological variations are very strong as opposed to the upper ocean, where things vary slowly and on large scale. But this model would say that if you look at the number of species, then that's not necessarily true. Plus, there are many regions like the Mediterranean and the warm regions here in the South China Sea, Java Sea, and so on, which have very high abundance of species in the surface as well as at the bottom. These are the regions where you also have very interesting behavior in terms of red field ratios or deviations from them and so on and so forth. So anywhere you look and everywhere you look, there are interesting questions from physics, from biology, and how biology and physics must be interacting, and how environmental forcing and interactions are creating niches, and how selections are happening, and how these selections are changing with respect to global warming. Okay, so again, nature makes the rules, biology finds the loophole. So it is very, very, very important that you learn to understand the loopholes or refugia and how they get formed, where they get formed, which species are able to exploit them, and what we can learn from them. There are very good examples of corals in certain regions like the Red Sea and the Caribbean, responding very nicely to warming because they adopt high temperature tolerant symbiont phytoplankton, and they can survive. And there are some that are not doing so well. So can you take genetic material from corals that are responding well and implant them into corals that are not doing well to save the corals that are not doing so well? So there are ideas that are infinite that you can think in many directions, but you need baselines. Ecosystems in general suffer from lack of baselines. So when people say species went extinct and then 10 years later we say, oh, we found it again, we are always dealing with baseline issues. This paper here uses statistical reconstruction of past climates. So going back to 335 million years ago, 69 million years ago, and 5 million years ago to understand how species have survived or gone extinct based on thermal breaching of their habitat preference, geographical range, size changing, body size changes, absolute thermal preference, and so on and so forth. I won't go into the detail. Basically, I'm saying that you need to establish baselines somehow. This is a good example of how we can go back way back in time, use paleo data to try to estimate how species are surviving or not based on where they are and what kind of climate impacts they are facing, and what that means to the oceanic carbon cycle and ocean's ability to take up carbon, because that is going to determine whether the oceans and ecosystems will become attenuators or they will amplify global warming. This is a very big problem, very nice challenge. So you must try to see if you can somehow keep your eye on it, at least in terms of what papers are coming out, what new ideas are coming out, and so on. You will see a lot of papers that make epsilon progress. It's not bad, that's how the community works, but a lot of people work on just incremental problems. You don't have to necessarily do that. You can always keep big questions in mind, even as you're working on a small problem. Okay, so find new ways to quantify the impacts of warming, sea level rise, acidification, deoxygenation, and so on, and pollution, and so on and so forth. Okay. The other big thing that remains unknown so far is really the disease pressure. I'm again using this just as a prop. This is percentage of reefs that are stressed, and these are the years, and these are the percentage of the corals that are having diseases. So proportion of Caribbean reef pixels exposed to bleaching level heat stress, there are various thresholds used here, and normalized disease reports for corals in the Caribbean both increase over time. But you can see that you can say reef stress is increasing, diseases are increasing, but you don't know whether this is an increase or if it's a regime shift, and whether this is a decadal variability, because if it is a decadal variability, it means it may come back down. Many ecological systems have regime shifts like the anchovies, sardines, and so on. The trick, of course, is to know intrinsic timescales and how global warming will modulate this intrinsic timescale. A 20-year cycle that is natural may become 30 years or 40 years, but it's still important to know whether it will come back or if it's just headed into la-la land. So you should always keep your mind open about whether, this is claiming to be a trend, but are you convinced this is a trend or this is a jump and a shift? So you have to really be careful about such claims as well. The other thing is not to jump on bandwagons. Now, everybody is claiming that there are heat waves in marine systems as well. The first person who defines this is going to get a lot of hits, a lot of citations, because he simply takes temperatures, defines 95th percentile as a heat wave, and he says heat waves are occurring in the ocean and they are increasing. And then there will be a million papers saying, yes, I found heat waves here and there and there and there. It's important because this particular infographic is also claiming impact. So here, for example, the warming is potentially related to El Nino, and coral bleaching in the Andaman Sea has been seen because of these heat waves. This is, of course, the El Nino pattern, and so on and so forth. So unless there are impacts, what will the marine heat waves do? We don't know. And let's say we found a way of predicting them. What are we going to do about it? If there is a heat wave that's going to happen here, do we have a way of protecting corals? Do we have a way of protecting fish? Or do we have a way of planning to prepare for the impacts, and so on and so forth? So the action that follows the claim of a heat wave also has to be thought of, and it's not a very simple problem. If you're going to tell fishermen that heat wave is coming, fish are going to die, so go and catch as many as you want right now, then can you collapse the fisheries because you are catching them at a weak point, and so on and so forth? So managing heat waves in the ocean is a tremendously difficult problem, and we haven't thought enough about it. It's hard enough to deal with early warnings and disasters on land. It will be much more difficult in the ocean, but we cannot ignore it. So we must track them, and we must develop impact-based indices and not just keep claiming that there are heat waves, okay? The other thing, of course, with the broad warming, we are going to have so-called tropicalization and detropicalization of species. So this is just a conceptualization of the species from this paper. And it is showing that if you look at the tropical species, warm water species, they have an optimum range and they have a distribution. And if you look at the boreal species or cold water species, they have an optimum range and distribution, which overlaps in this domain here. As warming happens, you expect the warm water species to spread north and become tropicalized. So higher latitudes become tropicalized. You will have tropical species expanding their range. And boreal species also may become more expansive in their domain. So you may have deborealization happening in some cases, and some of the warm species may be spreading and becoming borealized, right? So these are just words, but still it tells you that on land, we are observing butterflies are going to higher latitudes, marine species, some tree species are going to higher altitudes and higher latitudes. You have so-called mobile generalists and sedentary specialists. So when you have an ecosystem, the ecosystem doesn't move. Some species who are mobile and generalized in their adaptation or genetic adaptation, they can move. Some species will stay and go extinct, and so on. So you have to understand how the species distribution will change and how the species composition of ecosystems will change and how the entire food web will change with warming. In the meantime, you can go back to the bottom of the food chain and look at ocean chlorophyll trends for 1997 to 2021 here from Copernicus. And does it make sense? It shows that there are many regions with negative trends and many regions with positive trends. Surprisingly, much of the tropics have negative trends. Remember, we had a cooling trend here under global warming. So there is some little increased chlorophyll, but not very strong compared to the cooling trend. And there are loss of phytoplankton in various places. Coastal region here has become much more abundant in phytoplankton, but higher latitudes where spring blooms are the dominant mode of production have seen an increase in chlorophyll. So what is the dynamics? What is the ocean response to warming? Or is it related to the cooling that we saw here and the associated circulation changes? Or is it the North Atlantic Oscillation and its impacts on the cooling here, and so on? Mediterranean shows some increasing trend, and so on and so forth. And the Southern Ocean, which is very special, shows an increasing trend as well. So to understand the global warming patterns, ocean response patterns, nutrient supply patterns, and phytoplankton responses, and how it translates to primary production and upper trophic levels is quite a challenge to go from here to the upper food levels where we may be catching fish, for example, tuna, anchovies, sardines, whatever species we have, right? So you can see all the links you have to make in your mind, in your work, or at least always read the literature with these kind of questions in mind. Don't get down into too deep into just one area. Okay, so ultimately, to actually have actions and so on, you want to be able to use the so-called IPCC framework for defining risks. So risks are a multiplier of hazard, vulnerability, and exposure. So this is again done for plastic pollution and impact on ecological systems. And these are the hotspots where risks are high. So here are the risk scores going from 0 to 5. So these reddish areas are getting towards risk of 5, which is high. And they have vulnerability of megafauna groups or habitats. They have hazard from abundance of land-derived plastic litter, and their exposure comes from distribution of megafauna groups or habitats. We know that 90% of the fisheries occur in coastal regions, so obviously that's where you have high exposure possible as well, right? So it gives you a sense of how to go from physics, how to go from physics to ocean circulation, take the plastics into the ocean circulation and see where they're going to congregate and how that maps onto megafauna groups and how that affects their vulnerability and exposure and the net risk that you create from this kind of thing. So this is very, very critical for understanding what we need to predict to deal with the risks and how the risks are evolving over time. We are not anywhere close to reducing the plastic menace, but in the meantime, maybe we can map the risks and try to understand how to deal with the risks. I'm getting kind of close. I'm going quite fast, but I'll leave 15 minutes or so for questions. This is a nice paper from Stansted, already a few years old, but it shows nicely how you look at something like the North Atlantic Oscillation Index. If you don't know what that is, you can go on my YouTube channel and figure it out. Basically, the circulation over the North Atlantic and the pressure oscillation between the Icelandic low and the Azores high changes the storm tracks and precipitation versus storms and dry conditions and so on. And they nicely look at how the food chain gets affected. So wind patterns are affected by the NAO, and that affects the cloud covers as well, which affects the phytoplankton, photosynthetically available radiation, phytoplankton abundance, primary production, which affects the zooplankton, which affects not only capelin and herring through supply of food and for predation, but temperature and sea ice extent also begins to affect the range and abundance of capelin and young herring, and the cod that feeds on this is going to be directly affected by food availability as well as temperatures and wind patterns. So spawning, recruitment, everything is affected by that. Even on land, there are examples of collared flycatcher and pied flycatcher and how each one responds to high NAO versus low NAO and so on and so forth. Okay, so this gives you a sense that we are not only affecting the marine ecosystem just at one level, we are affecting it at every level, which means the entire food web is going to be perturbed at many levels, which means the role of the marine ecosystem in the carbon cycle and its overall productivity is being affected at many levels, which means the ocean's role in global warming through direct circulation changes and warming changes, heat content, heat uptake changes, and carbon cycle changes remain a big challenge to understand. This is something that really needs lots of attention. Models try hard. They are not getting into these kinds of details, but they do a lot of things. You can take outputs of some of the best models and try to analyze many of these links in the food web through not only temperature and wind, but also acidification and deoxygenation and so on and so forth. Okay, so I'll try to wrap up with ocean as a solution to climate change. Ocean is doing a lot of work and we're trying to exploit it more. So we should be careful what we do and avoid unintended consequences for sure. But I will take this from this report on 5 opportunities for action. So it talks about wind energy, how much offsetting mitigation potential there is by 2050 or so. Internal shipping also can be controlled in a way to mitigate emissions. You can do aquaculture, which not only helps food security, but also can put away carbon or reduce emissions at least. Domestic shipping as opposed to international shipping. There is wild capture fisheries, which has potential. Ocean energy is an abundant source, but we must do it without harming the ecosystems. Of course, ocean can provide offshore solar as well. Seaweed is a very interesting thing. It's now there's an article going around saying seaweeds can survive nuclear war. We don't want to think along those ways, but mangroves and subaquatic vegetation can sequester 3 to 10 times the amount of carbon that land forests can do. They, of course, act as storm barriers, reduce erosion, they increase oxygen, they provide habitats, and they don't get burned down in wildfires. So blue carbon is a rich source of putting away more carbon into the ocean, okay? So these are the numbers on mitigation by 2030 and 2050, which I won't read because I'm running out of time. Now, the other big thing that is emerging is how can we put away CO2 into the ocean? It's called ocean carbon dioxide removal. So there are electrochemical processes, there are restoring living blue carbon, mangroves, seaweeds, and other things. Seaweeds, there are many experiments showing that if you feed seaweeds to cattle, their methane emission actually goes down. Seaweed is a very good source of food for many as well. So you can imagine what many co-benefits that will come out of that. Macroalgae cultivation is being pushed. Deep sea storage is, of course, a very good target. Macroalgae cultivation and carbon sequestration. So microalgae, you can do ion fertilization and so on and hope that they will sink away, which is not guaranteed yet. But macroalgae can be more easily sunk, and you have ocean alkalinity enhancement ideas, and of course, artificial upwelling and downwelling. I have detailed podcasts on these on my YouTube channels as well, if you want to follow up. But I will come really close to the end. Think of even more exciting things, new materials, new technologies, new miniaturizations, and you can produce live skins from artificial material now, embed it on a person, and have it talk to your brain, kind of the things that Elon Musk talks about. So you have many such solutions possible, wearable technologies. Imagine putting wearable technologies on dolphins, on fish, turtles, whales, and so on to measure things. We are now putting them, we are instrumenting them with these big cameras and so on, but maybe it can be done in a much more harmful way and much more abundantly with these wearable technologies and measure more variables as well. So there are infinite innovation opportunities if you are inclined to do these kinds of things. So you can do reversible, organic, and flexible things so that they disappear into the ocean. They are completely recyclable or biodegradable, so you don't have to create a lot of pollution either. Okay, so saving the world and saving the oceans is going to be real fun. You are at the right time to get into this field and have real fun, and you have to have an optimistic vision for the future and avoid all these doomsday scenarios saying there is a climate crisis and the world is coming to an end. Well, it's not coming to an end. We may face some issues and challenges, but you can save your future and learn from the old people how not to do things. Okay, so I ran through a lot of things, but I'll stop here and take questions, and hopefully somebody is managing the chat box and can guide the questions to me.
Yeah, thank you, sir. Thank you for the lecture. And we are open for discussion now. You may please put your questions in the Q&A box.
While we wait for questions from the students, if I may ask one, with respect to the biological, physical feedbacks in the climate system, you did mention the problem with the how one parameterizes turbulence in the climate in the circulation models.
Yeah.
And usually the circulation models are developed first, and then the biology is embedded in it, right?
Yeah.
So it's going to be really tricky to accept that presence of phytoplankton could actually modify turbulence. And then you would have to modify the turbulence parameterization.
Yeah. I think somewhere in 99 or 2000, we published paper, Marlon Lewis, Chuck McLean, myself, Busalaki, and so on, using the diffuse attenuation depths from CVIS to show how we can include it in models. And then I gave talks around the world, and now there is not a single climate model which does not include this parameterization. Ted, I forgot his name, from UCSP, he produced a more subtle parameterization. And so pretty much every model now includes it. And the challenge is that in a place like the Indian Ocean or any region where temperatures are warm near the convective threshold, half a degree change can make a difference. So we don't know the phytoplankton impact in those places, how they are, if you have before convection, SST is warm. When convection happens, there is winds and the SST is cool, but that comes with nutrient entrainment and phytoplankton response. So I suspect, and I have hypothesized this before, but we did some ocean experiments to show that this works, that actually the reorganization of SSTs following convection seems to depend on chlorophyll response. Okay, so how to do this in the models? Problem is that they have so many other issues that they don't get down to this level. So hopefully in 10 years, this will be inevitable that to get it very correctly, they will have to do this. And also works for cyclones and other things where you are churning up a lot of nutrients and creating very easily observable phytoplankton response. So Anand Ganadisekan did some heuristic work on that. So that's why I said whether oceans are attenuators or amplifiers, because overall, everywhere, like we saw the chlorophyll bloom response in the spring bloom region, it's a huge response in phytoplankton with global warming. What is it doing to the heat budget in those regions? Because it doesn't have to be general warming. Phytoplankton is very patchy, so you can get fronts, and the atmosphere responds very strongly to fronts in SST. So somebody has to match the fronts in phytoplankton with the fronts in SST and so on. So there's a lot of work to be done there, but not enough people work on this topic.
By the way, Raghu, the trends we find with the OCCCI are much weaker, especially for autocorrelation, and then you remove all these trends that are not significant. The result is very patchy and much smaller than what you see in some other work.
Right. Yeah. So, of course, there are the cloud. Sorry. Yeah.
Sorry. I might bring up the question of how resilient phytoplankton are and how how they are adapting rather than responding.
That's a bigger, deeper and harder question. But for me, the first order question is the surface response, but also the subsurface response. So how are the surface properties changing and how the subsurface chlorophyll response is changing? We have very little idea about that. So with cloud problems, we have enough difficulty tracking surface trends and so on. So you have done very careful processing to get a handle on that. But we are pretty much a black hole in terms of subsurface response, which could matter for the heat content, especially in the cyclone regions and so on. So, yeah.
Good point.
We have one question that has come up from Gregory Jean Baptist. Thanks for a really fantastic presentation. How could you apply all this knowledge in small islands developing states, namely the Caribbean?
Yeah, Caribbean is a very interesting place. It gets this Gulf Stream, the splitting, the loop current, everything you want is there. You have the atmosphere, ocean interactions, hurricanes, and you have sea level rise impacting corals, fisheries, ecotourism. You want to have tourism and so on. So I think I would apply this with the warming, track the acidification, sea level rise, coral damages, and also look at how the risk factors. So you can make a map of, you will have to make a map of vulnerability of each sector, the corals, the fisheries, the coastal erosion, subaquatic vegetation, and so on, and look at exposures. And then hazards are easier to track in terms of intensification of cyclones or sea level rise or warming, or heat waves, marine heat waves, extreme rainfall, and so on. So vulnerability and exposure are tricky to do, but if we don't do it, if we don't start now, in 5 years, we'll still be saying it's difficult to do, and that's really not a good idea. So I think somebody has to start right now to look at what indices will work best to track vulnerabilities of each sector and exposure of each sector, and how the hazards, vulnerabilities, and exposures are creating risks. So having a risk map at a very high resolution is going to be the best way to plan things. Attenuation, preparation of disaster management, mitigation of impacts, and so on. So it's a very good mesocosm of the world where all these interactions happen. People, natural ecosystems interacting with each other, natural system, health, and so on and so forth.
Thank you. No more questions have come up.
Maybe it's because it's 1 hour. Could I ask one more question if there are no others?
Yeah.
And I wondered what you feel about the tipping points in the ocean from a biological point of view.
Sorry?
Tipping points.
I'm not a big fan of tipping points. I think they are too heuristic, and by definition, they're not predictable. So biology, as I said, I think biology finds loopholes. So these tipping points are something that Europe sells hard, and they really believe in it. In US, it gets no attention, and I'm actually happy about it because I think it's being oversold a little bit because models don't do it. They're using the models to say when they may arrive. But of course, in the ocean, we have these regimes where, there's nice work on anchovies and sardines, but it turned out to be not a tipping point, but a decadal variability, right? So for me, we are often misinterpreting things, or you hit things. For example, when El Nino comes, the anchovy population is really down. If you go fishing at that time, you are able to create a collapse. It happened in 1973, and it took decades to recover. So you can create tipping points by doing the wrong things, and that comes down to not having risk maps or not using the information properly to manage fisheries or corals. The Great Barrier Reef is something we have to watch closely to see where it's headed and whether it's, because if you look at the 1997-98 response and how it recovered, it's hard to imagine that it's going to collapse. It has some resilience in it. There are some ways in which it responds by changing its symbiont algae and so on and so forth. So I would focus lab experiments on their genetic response, their symbiotic response, their thermal response, their salinity response, and so on. We don't understand so much, and then we throw this tipping point in there. So I'm always a bit nervous that we are not aiming at things we understand well instead of trying to raise flags about things we don't really understand. So that's my view.
Thank you.
That's an interesting explanation. Anyway, we have a question from Abul Qasim. How does the Northern Indian Ocean respond under future warming scenarios in terms of nutrient circulations as well as productivity?
Yeah, right now it is, there are two parts to this answer. One, I said that the Middle East is warming and changing winds and the Arabian Sea is warming. Bay of Bengal cannot warm more because it's near the convective threshold. So if you try to warm it, it will convect more, it will have cyclones, so the heat will be taken away. So the circulation changes are, on the other hand, related to how much heat is coming in from the Pacific through the Indonesian through flow. And there is a very, very fast time scale from the Southern Ocean into the Indian Ocean. Some work shows that that connection is as short as 10 years. So Southern Ocean is very unique. It's a channel, it warms fast, and the warming goes very deep, and that comes into the Indian Ocean. So Indian Ocean is like a clearinghouse for global warming. So we have to watch this very carefully. But what we don't know is it has a very unique kind of relation between oxygen and to P ratios and nitrogen fixers and primary productivity. So the baseline has to be established in terms of how the Indian Ocean ecosystem has survived the warm temperatures and how it has evolved and how it will respond to further warming. But is it, disproportionately large exporter despite being in such warm waters, right? So if corals go away, then what happens? If corals do okay, then what happens? So it's a complicated story, but I suspect it's a nice little region that has to be well instrumented, well modeled, and watched carefully to see what has happened in the last 20 to 30 years before we worry about where it's going in the future, because the future projections are completely wrong in the Indian Ocean. The models don't do the monsoon correctly. They don't do the Arabian Sea response correctly. They are not doing cyclones, of course. So I'm a little bit nervous about projections beyond about 10 to 20 years. So I would focus on the past to understand how it has responded already. So far, the news is not great, I would say.
Thank you. We have another question from Colin Smith. Risks are also related to inequality. Sometimes the impact of coastal hazards is much stronger in low-income areas than in high-income areas. How to include socioeconomic factors in your risk analysis?
Yeah, so vulnerability and exposure actually should have, it on land or even on the coast, vulnerability will have per capita income, the type of house you live in, and the type of boats you have, for example, how many assets you own, women's education, children, age groups, and so on and so forth. And exposure will depend on infrastructure, population densities, and so on and so forth. So, of course, climate is not gender neutral. Climate impacts are not equitable. It hammers women more, it hammers poor people more. So the other part that has been added in AR6 is you have hazard, vulnerability, and risk, but we also add response now. So the response part must completely take into account the inequalities and the vulnerabilities as well. So there are ways to do it. The question is, how do we do it, and how the last mile problem of government taking care of those things at community scale can work. So there's a lot of work to do.
One more question has come up. There has been a lot of attention on the possible collapse of the AMOC in recent months. What is your opinion on that? Are the models able to simulate it accurately?
That claim is complete garbage. It's wrong. So I wouldn't bother with it. AMOC collapse is nonsense. So I showed that it's cooling in that region. There is no reason to believe it will collapse anytime soon. The headlines were all wrong, and they have taken one. I mean, I have written an article somewhere on it. It's just, I think it's irresponsible what was done. Many scientists have pointed it out, so I would not bother with it. Anyway, they can send me questions afterwards as well, if they, or you can collate them and send me.
Really, thank you, Raghu, for a really inspiring talk. I love the graphics; they're very clear and telling.
Thank you.
Clearly inspired the listeners. We had a good attendance today, so you've set a high standard for TPSF, and really appreciate.
I've shared the PDF with Jose, so you can distribute it to the attendees if you want.
Oh, that's great, because I was going to ask you for the PDF because they're so nice. Okay, thank you very much. And let's stay in touch. Thank you to all participants. Glad you enjoyed this talk. And of course, given Raghu Murtugudde's communication skill, we didn't expect anything less. So I'm glad you all attended. Thank you very much for coming. We'll keep you posted about the next one coming up. It should be a very different one. We are thinking about doing one on mapathons. So.
Thank you, Shubha. Thank you,
you.
Jose. Thank you, Nandini. Bye-bye.
Thank you.
Jose. Thank you, Katharina.
Thank you, Jose. So this was done with the help of Air Center, and we are very grateful to Air Center for continuing to support us. First, it was for our onward lectures, now for TPSF lectures. Thank you. Thank you, Jose and Katerina. Thank you.
Thank you. Bye.
Bye.
Bye.